Map matching is the invisible engine behind every accurate navigation app, autonomous vehicle route planner, and smart city traffic system. But it has a fundamental flaw: raw GPS data is messy. Multipath effects, signal blockage, and low sampling rates create trajectories that drift wildly from reality. Traditional methods try to snap these points to roads using geometric distance or hidden Markov models, but they break down in complex urban canyons. Modern deep learning approaches, like transformers and graph neural networks, promise more, but they come with their own baggage. They're often locked to the specific road networks they were trained on, making cross-city transfer nearly impossible. They also struggle to balance fine-grained local topology with long-range path dependencies, and they operate as black boxes. Today, we're breaking down a new framework called SceneGTMM, which solves these problems by combining conformal geometry, dual-graph neural architectures, and structured probabilistic modeling. This isn't just another incremental improvement. It's a fundamentally different way to represent spatial data that enables true transferability, robust noise handling, and interpretable decision-making. Let's quickly establish why this is hard. Early map matching relied on handcrafted rules. Nearest neighbor projection ignores road connectivity, leading to impossible jumps across highways. Topological methods like Dijkstra-based matching assume drivers always take the shortest path, which fails in real-world traffic. Then came probabilistic models, like hidden Markov models. They optimize emission and transition probabilities, but they assume noise follows a fixed Gaussian distribution, which urban positioning noise simply doesn't. Sequence-to-sequence models and early GNN approaches improved representation, but they remained bound to the training dataset's road network IDs. Change the city, and the model collapses. Transformers introduced global context modeling through self-attention, allowing end-to-end learning of driver behavior and spatial noise patterns. But they lack explicit topological constraints, struggle with sparse trajectories, and offer zero interpretability into why a specific road segment was chosen. The core contradiction remains: how do you balance local topological precision with global sequence modeling, while remaining completely decoupled from absolute geographic coordinates and training set road IDs? SceneGTMM's first breakthrough is a preprocessing paradigm called the conformal mapping scene relative strategy. Instead of feeding raw WGS84 coordinates or projected plane coordinates into the model, the framework dynamically extracts a local subgraph around the trajectory and maps it onto a unit disk using conformal geometry. Specifically, it leverages the Schwarz-Christoffel transformation. This mathematical mapping takes a polygonal region representing the local road network and conformally maps it to the interior of the unit disk. The key property here is angle preservation. When you transform the road network, the local intersection angles, turning directions, and relative connectivity remain mathematically intact. But more importantly, it completely strips away absolute geographic dependencies. The model no longer learns that a specific latitude-longitude pair corresponds to a specific highway ID. Instead, it learns relative geometric and topological patterns centered on the trajectory itself. During training, this unit disk coordinate system dramatically improves numerical stability. Gradient propagation becomes smoother because all spatial features are normalized to a radius of 1. The loss curves converge faster, and validation accuracy spikes earlier. In practice, this means a model trained on one city's road network can be directly applied to another without retraining, because it's matching against structural patterns, not memorized IDs. Once the spatial data is scene relative, SceneGTMM builds a dual graph architecture to handle the matching task. The road network is represented as a dual graph, where road segments are nodes and adjacency relationships are edges. This is a crucial shift from traditional intersection-based graphs, as it directly models the connectivity drivers actually traverse. Node features are extracted using a VectorNet-inspired subgraph encoding mechanism. Each road segment is vectorized into a sequence of attributed points, processed through a multi-layer perceptron to capture local geometric features, and then aggregated into a global segment representation. This road graph is processed by a graph isomorphism network, which extracts high-order topological features through iterative message passing. Simultaneously, the trajectory itself is modeled as a separate graph. A trajectory road association matrix is dynamically constructed based on buffer distances, quantifying how strongly each trajectory point aligns with nearby road segments. The trajectory graph captures temporal transitions through GNN layers, while a transformer encoder models long-range dependencies across the entire sequence. The integration happens in the cross-graph attention mechanism. Road graph embeddings are injected into the transformer decoder as a dynamic candidate library. Instead of using a fixed vocabulary and standard softmax classification, the model computes dot product similarity between the decoder's hidden states and the road network embeddings. This allows the transformer to dynamically attend to relevant road segments based on the current trajectory context, effectively aligning the semantic space of the noisy points with the precise topology of the map. But transformers have a known weakness in sequence labeling tasks. They treat each prediction step somewhat independently and can struggle with strict local transition constraints. In map matching, you can't just jump from a northbound lane to a perpendicular ramp without following the actual road geometry. SceneGTMM solves this by integrating a conditional random field layer on top of the transformer. The transformer outputs emission scores, which quantify how well each trajectory point aligns with each candidate road segment. Meanwhile, the CRF dynamically generates a transition matrix based on the scenario-specific road network topology, encoding physical connectivity, turning restrictions, and directional constraints. The joint probability of a valid path is then optimized using the standard CRF loss function, which combines emission and transition scores. During inference, the Viterbi algorithm performs dynamic programming to find the globally optimal road sequence that maximizes this joint probability. This structured prediction layer doesn't just improve accuracy. It forces the model to respect physical road connectivity, dramatically reducing impossible jumps and providing interpretable attention weights that show exactly how trajectory points align with road segments. The results validate this architectural shift. On trajectory datasets with positioning drift ranging from 16 to 50 meters, SceneGTMM maintains an accuracy above 80%. More importantly, it crushes the transferability test. Traditional deep learning baselines like M-Traj-Rec, GraphMM, and TMMLGD completely fail when tested on road networks outside their training set, because their graph structures and vocabulary embeddings are hard-coded to the training region. SceneGTMM, however, achieves an accuracy of over 82% in cross-city transfer scenarios, outperforming even traditional hidden Markov models. When trained on high-noise data with 50-meter drift and tested on low-noise data, the accuracy drops by only 2.4%, demonstrating exceptional generalization. The mixed training setup proves that exposure to varying drift variances and sampling densities forces the model to learn shared, robust features of road network structure and trajectory road spatial relationships, without sacrificing peak performance on any single dataset. Path similarity is further validated using Jaccard similarity and BLEU n-gram matching, confirming that the model preserves both segment-level accuracy and sequential continuity. SceneGTMM represents a significant step forward in spatiotemporal sequence modeling. By decoupling spatial representation from absolute coordinates through conformal mapping, fusing local topology and global context via a dual graph architecture, and enforcing physical connectivity through structured CRF prediction, it solves the long-standing bottlenecks of noise robustness, cross-regional transfer, and model interpretability. The framework doesn't just improve map matching. It establishes a new paradigm for how AI systems should interact with dynamic, real-world geographic data. Future work is already looking into multimodal sensor fusion for real-time traffic perception, lightweight edge deployment optimizations for vehicle-mounted computing, and neurosymbolic approaches to further enhance decision transparency. If you're working on autonomous navigation, urban computing, or spatiotemporal AI, this architecture is worth studying closely. The full paper details the mathematical derivations, ablation studies, and implementation specifics. Check the description for links, and let me know in the comments how you think conformal geometry and dual graph attention might apply to other spatial AI challenges. Thanks for watching,